So those were the kind of the targets. And what I wanted to do in my talk, so we approached this as so this is a research consortium. There was about 30 of us, plus or minus 5, over the course of this sort of 4-year period. I would say almost none of us had any real experience in, properly doing like engineering-driven long-term deployments. So a lot of this stuff we made up as we went along. And actually, it's probably fair to say that at the time we started doing this, there were very few examples of mobile autonomous service robots like this out there in the wild doing things. There were a couple of examples, but in these kind of unstructured environments, it was pretty new. I think nowadays that's no longer the case. There's lots of commercial ventures doing things like this now. So we had to learn a lot and invent a lot as we went. The other thing, which is probably common to a lot of people in this crowd, is that we were doing it as a research project. So our staff members were faculty, postdocs, master's students, PhD students. So we didn't have professional engineering support. We had people that were working on like fielding and deploying these robots alongside trying to get their papers into ICRA and IROS and all the other stuff we do. So, there'll be things that probably I talk about that some of you just go, well, that's just dumb. You should have known that in advance. But either it just wasn't our field of expertise, or we were picking this stuff up as we went along. So what I wanted to talk about really was I'm just going to restart these videos. I'm going to talk about, I think, 4 concepts that felt like particular challenges for us, and I'm going to use them as sort of headlines of things that we had to learn lessons about. And those lessons might apply to you, the things we learned from them might. And I must confess, I've kind of thrown this together reasonably informally, because I think it's going to just be easier if I talk rather than have good slides. And I'm very, very happy to take lots of questions. So some of the things the challenges that we felt were reasonably special to us, and maybe that's not true. I think everyone probably thinks that they're special, but there you go. And so when we were working on this, that one of the main challenges we had is that we deployed these robots over multiple different environments, and we had to go to these environments and deploy and set them up quickly. So we wanted the same software stack, the same hardware stack to run in environments that were reasonably diverse. We had to deal with these unstructured open worlds. So it was a closed world in the sense that we had a fixed map and a fixed spatial extent of the environment, but it was very much open in terms of the way that the world behaved, right? There was no way we could predict all the human behavior, all the objects that would appear in these environments in advance. So it was truly open in terms of the dynamic content of the environment, and actually in terms of some of the structure as well, as we'll see later. This idea of doing long-term autonomy without any direct engineering support on site really made us have to do a lot of things that we hadn't considered in advance, but I think we learned a lot from that. And finally, as you can see, there's people are a large part of what we're doing here in this kind of field robotics work. So we have to build robots that can act around people and increase. I think the main messages there for us were about how we work as researchers and scientists when we go into a populated space with robots. It wasn't necessarily about human-robot interaction. It was about researcher-human interaction. So that was maybe some of the lessons. So I'm really going to fly through this to try and get through everything in about 20 minutes and then take time for questions. I just want to give you brief examples of some applications. So we had the one in the care environment. We used the robot as a mobile information terminal. The robot would autonomously choose to go where it could access the most people and share information with them. We also had a robot acting as a tour guide. So the robot would wait at reception. People would come and enter the destination they'd like to go to, and they would then be taken to that location by the robot. One of the things that we did was we worked with the nursing staff at this care home. So this is Haus der Barmherzigkeit. It's a kind of mixed sort of hospital / residential care facility in Vienna, and had the robot supporting nursing staff running walking groups. This is a hiking group that went around the facility twice a week. And we had the robot, as requested by the nursing staff, kind of engage and support the residents in that place. In the kind of security, we did lots of work on trying to detect changes and new objects and learn objects, because in the security setting, kind of understanding environmental change in terms of objects is something that was quite important to them. And we also tried to do the same with human activity. So trying to detect when people were behaving in a kind of unusual or suspicious ways, given what we'd seen before. So lots of observation, lots of work on kind of learning from data, perception challenges, zero physical interaction, because that's this is hard enough. Physical interaction in these unstructured spaces is even more challenging. Okay, so those are some examples of tasks. So what I'm going to do is I'm going to kind of go through some of the lessons we learned and just kind of pop up really.
But I didn't have both.
Show you some of the things the lessons we took from that.
The axe might have worked.
Oop, is that someone asking a question, or is that someone with their mic on? I think that's someone with their mic on. Okay, so the kind of the first major problem we found, and I'm going to say this is a problem we found, this is something we sort of devised and then came back to later, is that we really wanted a way of deploying our robots into the target environments which didn't require expert intervention. So when we went to a new site, we didn't want to be able to have to take or have access to everyone that wrote all the code or developed the software or the hardware. So I think, developed a process quite quickly that meant we could go to a new setting, so field deploy our robot, but do it with limited expert support. So what we were able to do is kind of have a workflow that we could give to, in fact, even an undergrad. Undergrads were probably actually smarter than most of us. So give it to an undergrad or a master's student or a PhD student, they could turn up and they could deploy the system without needing access to the experts or recompilation. Our robots mostly did navigation, so our approach for that was based on a topological map. So this structure you see here, so this is trying to capture everything in one go. We're looking top down on a 2D map, on a map built by Gmapping that our robots use to navigate. And then we would manually annotate on top this graph structure. So this is an absolutely classic thing in robotics. It's a very standard approach to take in mobile robotics at this kind of scale. But the key factor for us that made this useful is that when we put this graph on top of the continuous map, we could annotate the edges in the graph with actions the robot needs to perform. So this allowed the robot to know in a kind of configuration layer the correct mobility, the correct actions to perform. And we could also do the same for nodes. So the robot would know what actions what it was capable of at particular nodes. So this is a very kind of model-based action, sort of state action abstraction of the robot's behavior. But rather than thinking of it, I mean, I think of it as a tool for planning robot behavior. But crucially for us, it's actually a way of injecting application knowledge and domain knowledge into our general purpose system at a very high level. So we could basically script the way the robot needed to behave at certain places and at certain times, really by just configuring this graph structure. And we had some excellent tools that we could use in RViz and in Python just to configure this very, very quickly. So we would build a map, and then we could have people drag and dropping these nodes and these maps to allow you to configure the way the robot behaved. So this key idea here is that every environment was different and required special purpose things for the robot to do, but we didn't want to have to write those in code, right? We wanted to be able to just configure the systems from a high level to do the right thing at the right time. So this is something, and I'll do this for a few. We've taken this idea forward. So we've started doing this in sort of 2013, 2014. We're still doing it today. So actually recently at RRI with Maurice Fallon and Yanis Vutis, we've been putting these kind of graph-based planning abstractions onto legged robots. And this just shows us running a similar kind of setup, so a topological graph with different actions and use for planning with Spot in our lab. So, where our mobile robots were understanding where doors were and how to move through narrow gaps, we're now using it to plan motions and detect obstacles with legged robots to know, when you need to change gate or when you need to go upstairs and things like that. So it's a great way of configuring your environment. So this unstructured world environment, and also the aim to do long-term autonomy without direct supervision, meant that, and this is a lesson for all field roboticists, failure is inevitable. So given our considerations, we knew from the start that we would inevitably encounter situations in the world, in our software setup, in our hardware, that we didn't consider at design time. And there's kind of one bit of the world that says, okay, well, I just need to make all my algorithms better. I need to put more special cases into every algorithm. I need to analyze in depth everything that's going to happen. But by definition, that's impossible, right? And there's massive diminishing returns on that kind of approach. So we took a kind of a sort of recovery-based approach. So what we wanted to do was to allow our systems to fail gracefully so that they could live to fight another day. And for us, what that meant is our robot needed to be able to be either escorted or pushed or autonomously moved back to its own charging station. If our robot ran out of battery, then we were really in trouble. We wanted our robot really to run every day without supervision. So if a failure was occurring, what it should do, it should stop and ideally not get into any further trouble, and then find some way of recovering and mean it could carry on. So I would advise anyone who's dealing with these kind of worlds to really put in some sort of high-level failure detection systems that look at things that we all know are sort of symptoms of failure. So things like timeouts, retries, the robot trying to do the same action again and again and again, or high uncertainty in your localization system. So things, or your perception system. So there are things you can detect that give you a good clue that something's going wrong. You can also think about kind of topic rates in ROS and things like that. And when you detect those things, I would advise against trying to fix the cause, but instead just trying to enter a safe state. So having the robot go, look, put his hands up and say, I'm stuck, please help me, and request human intervention then. So that allows you to really be robust to all sorts of failures, and then to kind of trigger recovery processes and call in help as needed. We had to deal with this a lot in navigation. So we had a lot of different types of navigation failure. The robot would get stuck on obstacles when its bumper would be pressed. Humans would place obstacles over things like its charging station to stop it completing actions. And the robot would have to pass through doors and have to wait for long, unpredictable periods when doors were opening and closing. And so we really put in detection and failure systems that would just really flag up and detect when these kinds of things were happening. And our recovery behaviors were very, very general. So our recovery behaviors, this isn't a video of recovery behaviors. I don't actually have one of those, which is annoying. But it's a map that shows where failures happened and the kind of things that we did to recover them. So in our case, we had two types of recovery when the robot would just ask for help. So it would just get stuck and say, please help me. And it wouldn't try and do anything else. It would just wait for humans to help. And it could ask for help via the screen. It could ask for help via voice. And as things got more and more desperate, it could send us email and it could send us tweets. So we really tried to get it to ask us for help. We also had some more autonomous things, so the robot could retry, just clear its cost maps and try again in navigation. And we had this quite nice approach of backtracking. So the robot knew the last couple of actions it took, and it was able to safely retrace its footsteps. And that allowed us to autonomously recover from failure, at least in navigation, in a number of cases. So these are very broad. They're not really trying to fix the problem of not being able to localize or pass through a particular location or complete a particular task. It's really detect failure, flag that something's gone wrong, and try and enter a safe state. And that allows your system to fail gracefully. This allowed us to recover in a range of cases. In one of our deployments, we had a failure of this nature like once every sort of 60 meters of autonomy. And we needed to recover from that. So it really helped us out. Right, I'm a little bit because I'm definitely not going fast enough. The other thing we learned is that log all this data, right? Our robot is running, because our robot is running without us there, we can't see what's happening. We need to log data. So when these failures are, we could look at the aggregate statistics over some of these failures that were occurring. And if we looked at them over time, you'd start to see peaks. And when you see peaks, what we could determine is that something major was happening. So a human had come in and reconfigured the environment, or something important was happening, the motors were failing and things like this. So we can look at our data and actually match some kind of peaks in these kind of events to things that we needed to actively try and fix, whether that was in the environment or whether that was in the system. This is a lovely example, which is worth talking about. So this work, one of the really active participants in this was the University of Lincoln, team led by Mark Hanheider. And here, what we see is a robot. We logged all our ROS bags as much as possible. This is a robot being pushed aggressively by a human that didn't like the robot. So we had a small number of localization failures. And it turned out that many of these localization failures occurred after the robot was stationary, which seems counterintuitive. But actually what was happening is a human was coming in and pushing the robot. And we were able, and so the team from Lincoln, with a guy called Tom Krajnik, who's now in Czech, built a system that could detect when the robot was being pushed. And the simple solution was to unlock the brakes or to turn off the motors, and the robot would move fluidly. And that allowed us to then detect when humans were pushing the robot and stopped us having all sorts of problems. The key message here was we couldn't have done that without having the logs of the data. So again, it's probably obvious, but when you're fielding your robot, it's autonomous and you're not there to supervise it, you need to be logging that data. But you also, if you're there for a long time, you need to be kind of thinking about triggers to record that data from failure, for example. Given that this is kind of an anecdote-based presentation, this is my other favorite anecdote. This glass doorway was not present when we deployed the robot. So this robot was running for about 3 months in this site. And one of the other large clusters of failures we detected was in this space. So the robot used to drive through this area unhindered. And then one day we got a phone call saying, well, Betty's really struggling with the new door. And I was like, what, new door? And because the robot had been so good at waiting at other doors while humans opened them, they hadn't thought to tell us or even ask us to restart the robot when they got some contractors in to install a new glass doorway in the robot's environment. So again, this was something we were able to detect because the failure rates for navigation in this area went up in a fairly large way. Okay, I'm going to keep plowing on. This kind of logging starts to lead us towards thinking about remote monitoring tools. So the sites we were working at were actually a long way away from where our experts were. So it wasn't just that we were next door and sitting on our hands, it's that we were kind of a long travel journey away from where our robots were deployed. And so we worked quite hard again with the team at the University of Lincoln to set up remote monitoring systems. So we had a web interface and a web setup where we could monitor our robot and task our robot. We also had a chat interface where you could actually see what the robot was doing and interact with the robot via chat. That made our life a lot easier. And again, this is something we're doing kind of currently with some of our inspection robots and field robots. So having a kind of web-based system where you can see what the robot's doing and task it really allows you to kind of beam in and see what's going on. And that's super useful. Okay, so again, so one thing to say is building these things takes time and expertise, but it's absolutely worth doing it. Okay, final slide in this very scattergun presentation, people. So a lot of our work was done around people, and a lot of these people didn't have a say about whether we were there or not. So one of the key lessons we learned from this was to work with all the stakeholders on a site before we went there. Our robots really impacted people's lives. And I would say don't underestimate the impact the presence of a robot or autonomous system will have on the people who work at that site that you're going to. Whether it's a mining person, whether it's someone working on an oil rig, whether it's someone in a nuclear factory, often they see a robot and they get suspicious. They see research and they get suspicious. So really work on your messaging before you go to a site. Really work with everyone there and double check. So we had situations where we worked with the PR people and the managers, and they didn't tell anyone in the offices that there was going to be a robot there. So we thought people knew what we were doing, but we didn't. So it's really worth double checking that everyone's getting the message about how your robots are there and what you're doing, because you can really have a big impact on people's lives. Two slides or some images to show this. This was a lady that basically loved our robot and turned into the robot carer. So every day she would make sure the robot was all right. She was the first person to help the robot. And she was very sad when the robot left. So we got this robot Bob here to deliver her some flowers. This was a lady who had the robot inspecting her office. And as you can see, wasn't quite so happy with the continued presence of a robot in that environment. And what you see is when these robots exist in people's lives, they really take them to heart. So this was Christmas jumper day, and the people went out of their way to find a Christmas jumper and fit it to the robot. So people really are a big part of these kind of social robot deployments. And it's really worth spending extra effort to make sure that you interact with the people and make sure they're happy with the robot there. Final lesson, which I didn't put on the previous slides, but this is a very important kind of safety, health and safety engineering lesson. If something goes wrong, you need to act on it. So you may go, oh, you know what, I'm a smart engineer, I know the cause of this problem and it won't happen again, it was a one-off. But actually, you really need to take these things seriously. So if you learn some lessons from a field robot deployment, try to act on them as quickly as you can. So this is an example where we lost a robot down some stairs, and a few years later, we lost another robot down some stairs. Now, in many ways, the causes were different. They were kind of one-off causes, but the solution that should have been in place from the first case wasn't in place in the second case, and it would have stopped it happening. So you have to take these lessons seriously, because even if it's not as serious as losing a robot down some stairs, you will be kicking yourself if you do one field deployment, and then the next time you go on a field deployment, you make the same mistakes. So it's definitely worth you being very conscious and kind of aware of the lessons you need to learn, and putting in that extra effort to learn them. Okay, I think I've used enough time. I am going to stop sharing my screen and jump back here, and I'm very happy to take questions.
Thank you very much,
That
Nick.
was quite quick and scattershot, but hopefully it gave you some things to ask me.
No, that was a fantastic presentation. Thank you. I've taken notes of lessons, nuggets of knowledge that you've given that we'll be collating throughout today's session and adding to the website. Does anybody have any questions right now? You can either type them in chat, stick your hand up, or type them into the Slack workspace as well. So we'll just give it a minute if anyone is typing.
I should say that I'm happy. I could talk all day about this, and if you want me to at some other time, if anyone in this audience wants to set up a call and wants to learn things, I'm very happy to talk about it. We learn a lot really by doing, and I'm certainly not a field robotics expert, but I'm someone that has a lot of painful experience about managing these kinds of deployments at this point.
It's interesting that you say that. 4 years of deploying robots in what could be quite viewed as a hostile environment insofar as it's full of people and they like shoving. If that doesn't make you a field robotics expert, what does?
Yeah, close experience. It's worth saying that the person that was pushing the robot was so that was outside a chapel, and the person pushing the robot was the priest. I don't know what the correct term would be, but so he was very upset the robot used to stand outside the chapel at certain times of day, and so he was very unhappy. There's a question about more about the remote monitoring tools. So yeah, we used we set up we used the ROS libJS system so that we could expose everything we needed into a web page. And so we built a web page that could expose, we could see the robot's current task list, we could view the cameras, we could view frame rates from the sensors and things like that. And then we needed smart people to make sure that we could view it outside. So getting that kind of web system set up isn't super difficult, and there's lots of kind of CAN systems out there that you can use to do that. The biggest headache and the thing we often suffer with is lacking the networking expertise to make sure that I can open a browser in my office and see inside the robot. And so we ended up with someone that really understood, I think, reverse SSH tunnels was what we spent a lot of our time doing. But later on, we were able, if we've got friendlier environments, we're able to run VNC or something on the robot that we can access directly. So I think a kind of simple web-based system is usually quite straightforward to set up. Someone that knows a bit of JavaScript could probably do it in an afternoon, but then making sure you get the right kind of tools on there, the right access to the robot in our setting was quite challenging. There was a question, direct message to me saying, how much time do you spend teaching the robot to detect different objects in the image processing? So that was super interesting. It was open world, right? So we couldn't know what objects were there in advance. The first year of the project, we had a system. So this was 2013. This was just when kind of convolutional neural networks and things were starting to make their way into the kind of work that was being deployed on robots. But this was slightly before that. So we had a shape-based categorical object detector trained on web images, I think, or no, trained on a 3D data set, a hand-curated 3D data set, because we thought categorical detection was the way to go, because we knew the categories, mugs and monitors and boxes and stuff. That worked appallingly badly. Later on, we ended up using kind of I don't know, some deep neural network. I can't remember the right one of the early ones that was open sourced, and that was interesting. But the kind of, again, something trained on web data did not transfer super well to a 3D robot, and so the angles were and the views you got meant that you got a lot of weird results from those detectors. So things that have very high precision on kind of image data is less good on robots. So in the end, what we did is we learned. So we have a paper called Autonomous Object Learning from a Mobile Robot. And what we did is the robot would detect change in 3D scans and then actually drive around the object generating images And then the robot, one of the things we did on the site is the robot would have a blog that would post pictures of the objects that it had seen, and we'd get humans to label, humans on the site would label the objects, and then we would train an object detector to re-recognize those kinds of things. So we tried to actually learn objects on the job. We didn't have a huge amount of data for it, but it was a fun thing to do.
Nick, there's a question on Slack. I'll read it out. Thank you for the great presentation. Was there any conversational AI capabilities along with its guiding navigating capabilities for the robot? Or is it something you wish to incorporate in the future?
Yeah, it's future work. So people absolutely want to talk to that robot. And we used voice as a feedback mechanism. So the robot spoke to people to say, please push me, please open the door, please do this. And that was very useful. But we just didn't have the expertise in the research project to work on speech input or any kind of conversational. It would have been absolutely beautiful. But the kind of speaker general speech detection from a mobile system was super difficult. We had a few attempts at sticking mics and stuff on and doing it, but we never got anywhere. And it was nobody's PhD project in the consortium, so it didn't work. But it would have been lovely to have, because people want to talk, like in those settings, people want to talk to the robots. Even if they just want to say hi, they want to talk to the robots.
All right, so I think there are a couple more questions on the chat, but in the interest of time, I'll probably introduce Tom.
Yeah, I will answer the questions in Slack whilst listening carefully to Tom.